Okay, yeah. So welcome back. So Arpan, Kabiraj, on Teichmiiller Space. Over to you, Arpan.
Yeah. So today I'm going to talk about Teichmiiller Space. And so the way I want to present it is that you might have seen some form or some version of this in your geometry or algebraic topology course. And I will try to drag the analogy from there to explain why people are interested in Teichmiiller space and why people study Teichmiiller. So here is a setup that I want you people to keep in mind. And this you have, if you have done some kind of geometry or topology, algebraic topology course, you have seen this. So suppose you have a manifold or just a topological space, then you can consider its universal cover, and you have a group of Deck transformations. Okay. Now the analogy is the Deck transformation. If your space is nice enough, blah blah blah, everything is there, then under natural conditions, this will be same as the fundamental of your manifold. Okay. And so the group of all Deck transformation, this acts on the universal cover. So let me drag this here. This group of all Deck transformation, this acts on the universal cover to give you the quotient. There are three objects here. There are three players here. Here is a group. Here is a kind of a, let me write it down, an easy space. Easy meaning it has, topologically, it is less complex than the bottom one. Simply connected. You understand these things better in some other sense. And this is your third character, which is the, I will say, the main character here. So typically, the way we understand, start studying the things. The first theorem probably in algebraic topology we learn is the fundamental group of, so after first non-trivial theorem, is fundamental group of circle is Z. And so your main object is circle. And you want to understand what's this fundamental group. So what you do is you first go to the universal cover, which is real life, and you identify the fundamental group with the group of all Deck transformation that tells you Z. So that is the picture here. This is the Deck transformation, which is Z. This is your real line, which is universal cover, and this is your circle. Okay. Now, so there are three players here. Here is a group. Here is an easy space in some sense, and this is a main object. So now what happens is this action has some property. Okay. So the group of all Deck transformation acts on the universal cover, and typically this property is properly discontinuous action. And I won't go into this action pretty much. Sometimes there is a version of this. This is called free action. There are like bunch of definition on properly discontinuous depending on what type of space you are working on. One definition makes sense, other two definition will be equivalent, and so on and so forth. But is there anybody who hasn't seen some form of a definition of proper discontinuity? Anybody not familiar with this term? Okay, so I will assume you have you have seen the definition in some form, whatever form you are comfortable with, that's okay with. So there are three things here. So we have this group, we have the easy space, and we have the main object, and this action has certain properties, namely properly discontinuous. Now, the thing is, if your space have some kind of geometric structure, and this some kind of geometric structure, it's a very vast statement, but okay, give me 1 second. Screen is frozen. Can you see the screen now? Is the screen visible now?
Yeah.
Yes.
Okay. Okay. So now suppose your manifold, this manifold that you want to study, this has some kind of a special structure. Suppose it's a differentiable manifold. Then by the covering map, you can pull back the differential structure. So your universal cover, so this format, this picture which is written here, this is purely topological and group theory. You don't need much except some topological conditions, locally simply connected and all those things, but this is properly a topological picture. Now the more structure you give to your manifold, or you can gain from this picture. So if your map, if your manifold here has a differential structure, you can pull back the differential structure to your universal cover. So again, the universal cover will also be a differential manifold, and this group of a deck transformation will be a group under which group of all diffeomorphisms. If your manifold has Riemannian metric, you can pull back this to a Riemannian metric on the universal cover, and in this case, the group of all deck transformation will become an isometric. Okay, subset of the isometric group of the universal. So depending on the properties of the base space, this is I'm calling it base space, your information on the universal cover and the group will enhance. This is the basic structure of this picture. But pretty much always this properly discontinuity will remain in some form or the other. Okay. So now, what is our main object of study in all this mapping class, group, and Teichmiiller space? So the main object of study, which is classically has been studied from every sort of many perspective, is, so in this talk I will focus only on closed surfaces which do not have a boundary, so compact which do not have a boundary. So suppose S is a closed surface of genus G greater than or equal to 2. Okay. And so one of the properties of these surfaces, closed surface of genus G greater than or equal to 2, their Euler characteristics are negative, they admit a complex structure. So S gives you what is known as Riemann surfaces. Whatever that, it's a one-dimensional complex manifold. So every time you have this condition satisfied, you can put a complex structure on the manifold. Okay. So this gives you a Riemann surface. So it's an example of a Riemann surface. So the object of study, which is pretty much for a long run, and this word comes every now and then if you attend some kind of seminar. So the object of study is moduli space of Riemann surface. Okay. And so this moduli is kind of an interesting thing to say what the moduli mean. In some sense, just keep in mind, moduli means you have some kind of structure and you are trying to collect all possible structure. Moduli means a collection of structures given on this Riemann surface space. Now, what kind of structure, that depends on what you are studying. If you are interested in complex analysis, you are studying all kind of complex structure. If you are studying differential manifold, you are studying all kind of differentiable structure. If you are studying hyperbolic metric, you are studying all kind of hyperbolic structure in the manifold. If you are interested in flat surfaces or flat structure, you can study all the collection of flat structures also. It's up to you. So this moduli is a very vast subject, but by moduli I mean collection of structures on the surfaces. Okay. So why is it called moduli space? So let me say this thing a little more detail. This is called moduli space of Riemann surface. Now it's not just a set, it's a space, meaning it must have some kind of extra structure. And this is the interesting part. So this is one of the primary sort of give immediate, not immediately, it's a consequence of uniformization, that whenever you study the collection of structure on Riemann surfaces, it always comes with some natural structure. The set of all structures on Riemann surfaces, it always comes with some kind of structure. May have some algebraic structure, some differential structure, some Poisson structure. It always comes with some kind of Poisson structure. So this was the main object of study from like long back. And it's a space. You can actually give a topology to. That's pretty much easy. The moment you know what a differential structure is, or a hyperbolic metric is, or a Riemannian metric is, you know the collection of all of them sits in some big Rn, and you can use the subspace topology. So it's always a topological space. So this is our M. This is our M, which is here. Okay, so this is the modulus. Now, in this case, in today's discussion, by moduli, I will mean hyperbolic structure. Okay. So by moduli, I mean hyperbolic structure. Okay. So what is a hyperbolic structure? It's a differentiable manifold which has a Riemannian metric with constant sectional curvature -1. So we know that if Euler characteristic is negative, if your surface has genus G greater than or equal to 2, it always admits a hyperbolic structure. And there are a lot of hyperbolic structures. So this moduli space is a collection of all hyperbolic structures. So I will write it. This is collection of all hyperbolic structures. And this is up to isometry. So you consider two hyperbolic manifolds, two hyperbolic surfaces equivalent if they are isometric. Okay. So well, this is my space that I want to study. This has some importance. This has a lot of importance, pretty much. And once Yuri Ivanovich Manin said that any problem in mathematics is somehow related to some study of modular space of Riemann surface. So it's that important. Okay. So this is our study. This is our object to study. And as usual, you can understand, because it's so important, it's very, very hard to understand. It's extremely complicated. It's not even a manifold to begin. It has a topology, but it's not even a manifold. So any kind of information about this space is really hard to get. And so we are in the scenario that we have a main object we want to study, which is complicated. So to make things simple, I need two things. First, I need a group. And then I need a space, which is in some sense easy space, which has lesser topology. Now, in this scenario, where I'm considering a collection of hyperbolic metric, this group you people have already seen. This is the mapping class group. So this group here is mapping class group. So you have a group, have the space you want to study. So now only left is the easy space, which is simply connected, which has all the easy property. Easy is relative, easy in relative sense. And this is our main character today. This is the Teichmiiller space. So this is one of the many reasons to study Teichmiiller space. The universal cover, whatever that means, it's a simply connected space which lies on the top of the moduli space. So there is a quotient map from Teichmiiller space to moduli space, and it's covering transformation. If things make sense, if you put things in correct order, then it is nothing but the mapping class group. Okay. Why I said this thing is complicated is, the problem is this mapping class group you have already seen so far. This has finite order elements. Now, if you have seen some kind of group action on manifold unit, you know that the moment your group has a finite order element, your quotient is bad. It will not have any kind of manifold property. I mean, the moment you look at the orbit of the finite order element, they will give you what are known as cone points. They won't give you the manifold kind of problem. And that's one of the reasons why people actually study the Teichmiiller space directly. It's a nice enough manifold. So this thing here is a manifold. Unfortunately, this is not, and this is the group. Okay. So now, any questions so far about this picture? It's just a brief overview where these things come from. Okay.
Sir, what did you tell about Teichmiiller space? What is the definition, main definition?
I haven't. I will come to the definition now. I will come to the definition. This is just to motivate that where the Teichmiiller space is coming from. Okay. Now, yeah. So now let us go to the definition of Teichmiiller space. So remember, this is collection of all hyperbolic metrics. Okay. So now if you remember your algebraic topology course, how do you construct a universal cover of a topological space? And if you remember, you realize you take the loop corresponding to every loop, you construct a path in the universal cover. So it's like opening up the loop. Okay. So now if you look at this object here, this is a collection of hyperbolic metrics. So what is the loop here? So if you look at a loop in M, if you just look at some loop in M, what it will give you is a one parameter family of hyperbolic manifolds, which starts and ends at the same point. Okay. In other words, one parameter family and homotopy are sort of the same thing. I mean, homotopy basically means x cross I to something, which in the second coordinate you just think of as a parameter time. So homotopy is nothing but a one parameter family. Okay. So the loops in this manifold M, or not a manifold, in this set M, are nothing but one parameter family of Riemanns of hyperbolic metric. So keep that thing in mind. Ultimately, at the end of the day, what we are going to consider is collection of hyperbolic metrics. Okay. And then two metrics we will call equivalent if they are homotopic, and also so on. Okay. So that's the motivation of defining Teichmiiller space, at least from our point of view. Classically, it is completely different. So let me come to the definition. Yeah.
To make sense of this, we need to define any topology on a collection of hyperbolic structure, right?
Right. We can define. So what happens is, if you look at a hyperbolic metric, it comes from a Riemannian metric, right? And so what is a Riemann? If you remember the definition, it's a one parameter continuously varying family of inner product in the tangent space, in the tangent spaces. Okay. So another way to say this thing is, and this is, I'm just rephrasing the definition of Riemannian metric. It's just a continuous section of cotangent bundle cross cotangent bundle of the map. So again, this is just a function from the manifold to cotangent cotangent bundle product cotangent space product cotangent space. Now, given such a function, whenever you have two spaces, so cotangent bundle has a topology, the surface has a topology. So whenever you have a collection of topologies, collection of functions in a topological space, you can always give the compact pentagon. Okay, so that will give you a topology on this modular space. All the structures, this like, whenever you want to give a topology on some collection of structure, pretty much in this same line. You first write your structure in form of some functions, and in your function space you give the compact pentagon. Is that okay? Well, I just gave you the briefly where it comes from.
Yes, okay.
Yeah. So I won't go much into this because this is really complicated object. Okay. But yeah, just to keep that in mind. Okay. Any other questions? Okay. So now I will define what is Teichmiiller space, and remember this will be some one parameter family of hyperbolic metrics. Keep that in mind. Okay. So let me give you the definition. So first, so this is the definition. So first, suppose S is a closed surface. So S is a closed surface. So a marking, and this is I'm defining, marking phi is a diffeomorphism. So let's say marking X comma phi is a pair where X is a hyperbolic manifold. Let's say hyperbolic surface or hyperbolic manifold, doesn't matter. And phi from S to X is a diffeomorphism. Okay. So what is a marking? Marking is a pair where X is a hyperbolic surface. So what is a hyperbolic surface? It's a surface which also comes with a finite area hyperbolic matrix. Okay. So here I am just taking closed surfaces with boundaries. So I can take, okay, it's a compact surface which comes with a finite area hyperbolic matrix. Okay. And phi from S to X is a diffeomorphism. So basically what we can do is, what we are doing here is, we are providing a hyperbolic metric through a function to S, which is pull back the hyperbolic metric. Okay. So it's another way to say, it's another way of saying is, we are specifying not only a hyperbolic metric on a surface, but also some kind of an association. And I will explain where this association comes from. I'm trying to keep track of how we are associating the surface with the hyperbolic. This is the sort of important point, the mark. Okay. So this is called a marking. Okay. Now two markings. So let X phi and Y phi be two markings. We say they are equivalent if, so you have S, you have X here, you have phi, and you have Y here, you have C. And so what I want is, if there is an isometry I, so this is an isometry, such that if there exists isometry I from X to Y, such that, and let me see this so that I don't make the mistake. So I want I composition space is homotopic to so is it I composition space homotopic to size. Okay. Let's focus on this definition a little bit. So what have I written here? I have two markings, X phi or X phi or Y c, and then we say that they are equivalent if there is an isometry. So remember, X and Y are hyperbolic manifolds. So they are Riemannian manifolds. So there is an isometry. Definition isometry makes perfect sense. So then we say they are equivalent if there is an isometry. I composition phi is homotopic to C, not equal to. And so the reason, again, the motivation behind this, we are trying to consider homotopy classes of hyperbolic manifold. There's some one parameter families of hyperbolic manifold. And so this is sort of the kind of the background story there. This is why I am considering two markings up to homotopy, not up to exactly equal. So is the definition of marking and definition of equivalent marking clear? Any questions? Okay. So now I will define what is the definition of Teichmiiller space. So a Teichmiiller space of S So the Teichmiiller space of S denoted by Ts is defined to be Teichmiiller space of S is equal to collection of all markings of two equivalence. So this is same as collection of markings up to homotopy. Okay. So let me focus on this definition a little bit. So here is the setup. We have a closed surface. A marking is a pair. X is a hyperbolic surface and phi is a diffeomorphism. We said two markings are equivalent if there is an isometry. So such that this diagram commutes up to homotopy. Not exactly equality, but up to homotopy. And the Teichmiiller space is the collection of all markings up to equivalence. Any questions on the definition? The definition clear? Yeah.
Question
Yes.
is, you have defined the equivalence between two markings, right? So,
Right.
My question is, just can you show me an example or give me an example such that two markings are not equivalent, this type of thing?
That we will come. That will come. That I will come. So
Okay.
here is a hint. That's why I look at the. That's why I gave you the motivation here. When do two elements lie in the same lie at the same point? They have to lie in the same orbit here, right? So if you look at the quotient, yeah. So now if you take any element in the mapping class group and it acts on the surface, you will get another mark. So I have to define what the action is, but you get the point, right? So you pretty much pre-compose or post-compose by some, you see the action of an element of mapping class group on the hyperbolic surface, you will get another mark. It's just in some sense, makes sense in some way. I couldn't hear you. Anyway. Okay. So yeah. Any other questions? Okay.
Sir?
So now, yeah.
You have said that the modular space is the collection of all hyperbolic structure, right?
Right.
So there is no condition there up to isotropy or up
There's
to
no
homotopy,
condition
right?
there. You're absolutely right.
Okay.
There is up to isometry.
Okay.
Whenever you have
Here it is up to equivalence.
Yes, here is the. Yeah, Arpajit, it is. Yeah, Arpajit, there was a question. Yeah, up so far it's just a set. It's just a set, nothing more than just a set. I haven't told you whether it is a space or anything. Just a set. Okay. Yeah. So now I will go into the first kind of. I will give you some example, some motivation to explain what type of space we can expect out of it. What type of space we can expect out of Teichmiiller space where your surface is homogeneous. So I will show you what happens where surface is torus. So if S is a torus, so now suppose S is torus. So, okay, let me. Okay, I just want to tell you something. So here I am always working with hyperbolic metric, right? Hyperbolic surface. So torus does not admit a hyperbolic surface. So in this definition here itself, I am assuming the surface has genus G greater than equal to 2. But the point that I want to make is, suppose rather than looking at hyperbolic metric, you think of this as some kind of some structure, collection of some structure up to some marking or something. In that way, the Teichmiiller space of torus also makes sense, and we can complete. Okay, but let's not go there. That will be confusing. So I will go to the topology of it. Let me give you the description of the topology of what kind of topology it is here. So let's not go to the torus thing. So topology on Teichmiiller space. So now, as I said, that whenever I would like to put a topology on something, doesn't matter which object we are studying, if I want to put some kind of structure on collection of some structures, so some collection of hyperbolic metric, collection of differentiable manifolds, and so on, first I have to write them in a form of a collection of functions from somewhere to somewhere. So this is what I am going to do here. I am going to first write down the collection, the markings, as in a form of functions. Okay. So let's see how we can do this. So first of all, suppose you have given a marking x field. So suppose let x be a marking. Okay. So therefore, we have a diffeomorphism phi. So we have a diffeomorphism x from S to X. We have a diffeomorphism phi. Okay. So now X is a hyperbolic manifold. Remember, X is hyperbolic. It's a hyperbolic surface. So its universal cover is the upper half. So therefore, you look at the universal cover of S, call it S tilde, and you can identify these two. S tilde can be identified with the upper half. And how do you do this identification? How do you understand this identification? So first what you do is, you take the pullback of this metric of X to S via phi. Okay. And then how do you get a hyperbolic structure on X, where you identify the fundamental group of X as a group of all deck transformation of this covering map. So then the group of all deck transformation of this covering map will be a subset of isometric group of upper half plane. And via phi, what you are doing is, you are identifying the fundamental group of S with this. Okay. So let me repeat this. So phi, phi star gives you an isomorphism between fundamental group of S and fundamental group of X. Fundamental group of X is nothing but group of all deck transformation of, let's call it XE, which sits inside isometric group of upper half plane, and because it's orientation preserving, I put isometric group of upper half plane plus. Any question here? I'm just using that phi is a diffeomorphism, so I can pull back the hyperbolic metric, and pulling hyperbolic metric is same as saying that pi 1s acts as group of all deck transformation on the upper half plane by isometry. How do you identify that? How do you identify that subgroup? Well, look at pi 1 of X. That's the fundamental group of X. that automatically acts as a group of all Dick transformation. So therefore, you have phi, which gives you an isomorphism between pi1s and pi1x. So rather than identified pi1s, we look at pi1s as the group pi1x, and that gives you a Dick transformation that is sitting inside isometric plus of H2. And this thing we know is PSL2R. Okay. So in short, what do we get out of all this? We get a map, a homeomorph, a map of pi1s into the group of all Dick transformation, which is sitting inside isometric group of H2. So in other words, a marking gives us a homomorphism, call it something rho, from fundamental group of S to PSL2R. Okay. Now, just this is sort of like the precursor. I'm just trying to motivate that what is the information that we get from our marking. So each marking gives me a homomorphism from fundamental group to PSL2R. We have some kind of mapping. Okay. Now let us look at, well, I can give the topology right away, but let me just go to that a little bit more. So firstly, remember this pi1s and pi1x is isomorphic. And so the pi1x is also a group of all Dick transformation, which is a subgroup of isometric group of H2. In other words, this homomorphism that you get is an injective homomorphism. Okay. And I mean, the term in representation theory where you have an injective homomorphism is called a faithful. So rho is faithful. It simply means rho is injective. Okay. So whenever you have a homomorphism from a group to some matrix group, you think of it as a group acting on the some vector space, and the matrix group is sort of the linear transformation. So that gives you a representation. So homomorphism from pi1s to some subgroup of group of invertible matrices, you can think of it as a representation. So that's the terminology we are using. So that every marking gives me a representation or a homomorphism which is injective. That means the representation is faithful. It's the first thing. Okay. The second thing, and this is where this, remember the action of the group of all Dick transformation on upper half plane is by isometry, and the action is properly discontinuous. Whenever you have a genuine manifold at the bottom, action by group of all Dick transformation on the upper half plane on the universal cover is by the action is properly discontinuous. Now, what does that translates to? If I just look at this picture, what does that translates to? Well, here is a simple question, and this is where the term discontinuity comes from. Suppose you have two spaces x and y, and you have a function between x and y. What is the topology in y that will guarantee that the only continuous functions from x to y will be the constant function? So the question is, suppose you have given two spaces, two topological spaces x and y, and you want to put a topology in y which will make sure that no matter what function you consider x to y, the only way they can be continuous is they have to be constant. What kind of topology put in y which will make this?
Sorry, could you repeat your question? Your voice breaks.
So the question is, suppose you have two topological spaces, two topological spaces x and y, and you want to put some topology will in Y, which will make sure no matter what function you put from X to Y, it will be a it will be a discontinuous function, unless it's a constant.
One I do discrete.
It's a discrete topology, right? So you put the strongest topology you can put. It's a discrete topology. So this term discontinuity and discrete topology in some sense goes in parallelly in this similar fashion. So whenever you want all the functions to be discontinuous, the topology that comes to your mind on the right hand side is discrete. And this exactly happens here. So because this group of all Dirac transformation acts properly discontinuously, an alternative way to say that the Dirac transformation acts properly discontinuously, an alternative way of saying the same thing in a different format, is to say that this homomorphism has a discrete image. Okay. So because group of all Dirac transformation X acts properly discontinuously on the upper half plane, this homomorphism will have a discrete image. So rho is discrete. That means image of rho is discrete. I hope you people know what PSL2R is. Just SL2R quotiented by plus minus 1. Okay. Okay. So now here is the thing that this is the easiest way you can put a topology here is, now you have seen that every marking gives you a discrete and faithful representation of the fundamental group to PSL2R. So every marking gives you a homomorphism from pi1s to PSL2R. As I said, whenever you want to put topology on any space, think of the point as some kind of functions. And on the function space, you have always a topology, which is compact open topology. So now you put the discrete topology on pi1s, just a countable group. PSL2R, you have a natural topology. So set of all markings, you can simply give compact open topology out of this collection. So on the set of all markings, you can give this topology. So now you have extra one condition that we are considering, not just set of all markings, but equivalence classes of set of all markings. So you can just put the quotient topology there. This is one way. Straight away write down that this is the quotient topology. But let's say, is the topology clear? What is the topology in the Teichmiiller space? Every marking gives you a homomorphism, and these homomorphisms are discrete and faithful homomorphism. So just think of them as a collection of homomorphism, collection of functions from pi1s to PSL2R. Pi1s has a discrete topology, PSL2R has natural topology. So you consider this collection of all markings inside them that has a topology. Take the quotient under equivalence relation, you take the quotient topology. That's it. Is the topology, I mean, I won't say clear, but is the definition makes sense? Any question on the topology of the Teichmiiller?
Before taking quotient, the topology is compact open topology, right? On the all the maps. Right.
On all the maps, you have the compact open topology. And so this set of all markings can be thought of as a subset of all the maps. So that gives you a subspace. And then we go to the quotient. Okay. Any other questions? Okay. So now I will go to the fact that what happens in the quotient. What does this quotient really looks like? So let me write this down. So consider this space of all discrete faithful representations. So let me say that. Okay. So consider the collection Pf of pi1 of S, PSL2R. So this is the set of all, and now I can actually write space of all, because now it has a topology, space of all discrete faithful representation.
Is it? Because it is not the other way around. I mean,
I'm not saying this is Teichmiiller space.
I see, yeah.
This is just a collection on which has a subset whose quotient is the Teichmiiller space. I'm saying set of all markings can be thought of as a subset of this space.
Yes.
And because this has a topology, so I can consider a topology on the set of all markings, and then out of that I can get a topology on the quotient space, which is a Teichmiiller space. Okay.
Yeah.
So now we will look into the picture and we will see what happens to the quotient. Can I clearly identify which subset it is and what quotient it is? Okay. So now look at a mark more carefully. So here in this proof, we have seen that given a marking, I can construct a discrete and faithful representation. What about the converse? So suppose somebody gives you a discrete and faithful representation from pi1s to PSL2R. Two criteria, discrete and faithful. So what happens? Huh?
Yeah. The right answer is isometry of H2, therefore yes adds on H2.
Right, exactly.
Take
So
its
this
quotient.
is exactly. Absolutely. So now suppose you take a row from discrete faithful representations of pi1s to PSL2R. So then row will give you a homomorphism from pi1s to PSL2R. This is nothing but isometry of upper half plane. So then you can take this action via row. So in other words, you can take row of pi1 of s and you act it via this homomorphism on the half plane. And because the action, so first one is it's faithful. So that means this is actually a subgroup of isometric group of H2, PSL2R. So this map is injective. Secondly, it's discrete. And as I said, that this is a small technical point. We can discuss this in the tutorial. Proper discontinuous action is nothing but the image being faithful in the isometry. So the group of Waldeck transformation acting properly discontinuously is nothing but saying that this group of Waldeck transformation sitting as a discrete subgroup in whatever space we are talking, space of isometry is a space of Waldeck. Okay. So this discrete, so the image being discrete is same as this action be properly discontinuous. So therefore, you can take the quotient by this I1 of s and call this x, and this row will already give you a diffeomorphism. Okay. So therefore, whenever I have a discrete faithful representation of the fundamental group, whenever I have a discrete and a homomorphism from fundamental group to PSL2R, which is faithful, that means injective, and whose image is discrete, I automatically get a marking. First, I will quotient the upper half plane with the image of pi1s. Now, because it's an injective map, so therefore I can consider it as a subgroup of isometric group of upper half plane. Because the image is discrete, therefore the quotient will be, the action will be properly discontinuous. I can take the quotient to get a manifold, a hyperbolic, and this row will induce a diffeomorphism. So therefore, every marking gives me every homomorphism from pi1 s PSL2R, which is discontinuous, gives me a mark. So this space is nothing but space of all mark. Okay. Any questions? Okay. So now there are two things. I have to, so now there are two things. Well, I will, okay, let me put this thing in bracket. This is not actually quite true. So let me not put this thing in bracket. So I can just simply say that, okay, every marking gives you a discrete and faithful representation, and every discrete and faithful representation gives you a mark. It's the other way. So I'm just, as of now, I'm just saying that this is just a set bijection. So I'm not writing set of all marks. So I'm just writing set of all marks. Okay. Now let us look at the quotient criterion. Now here's the first thing that you notice. See, whenever you have representation, and I'm, yeah, go ahead. What is the map from pi1 from phi to s to x? Yeah. So the point is, if because of phi, because of pi1 s as a map into PSL to R, so call this subgroup H, let's say. Okay. So therefore, H can be identified as a fundamental group of X. H can be identified as fundamental group of X. Now the point is, if you have, and now this is an isomorphism, right? So the point is, if you have an isomorphism between pi1s and pi1 of X, because they're KG1, you can construct a map between X, S and X, which is a homotopy equivalence. You can define a continuous map between them. And because of the construction, this map will automatically gives you diffeomorphism. It will go the both way around. Okay. So yeah, there is a slightly technicality that I am avoiding here. Yes. So to construct this map phi, you need some work. Won't be direct construction, but you need some work. Yeah. But this happens because of surfaces. Okay.
What happened to the representation if two things are equivalent?
Yeah, so that's what I'm coming. Yeah, so that's what I'm coming. So now let's see how two things can be equivalent. So let's say you have, so this is a standard representation theory. This is where the equivalence of representation comes into picture. So suppose you have one representation into PSL to R, and you have another representation to tilde to PSL to R. But now what I do is, okay, so let me write it here. If you take an element of PSL to R, it's a group. So you take an element from PSL to R and consider the conjugation. So PSL to R acts on itself by conjugation. I'm not sure whether this is a good notation or not. So let me write down conjugation by. So IA means IA of B means A inverse. Okay. So now if you post compose I with rho, you will get another representation. Point is, you are not changing the hyperbolic matrix. If you just conjugate the upper half plane, but by another isometry, in a representation way, you are not changing anything. If you look at the group of vertex transformation, action of the group of vertex transformation on the upper half plane, you are not changing anything. You will get the same mark. Okay. So that so another way to say this is, if you have two markings, xp and let's say yc, and then they differ by, so if I take two markings xp and then y and some phi compose some isometry I, they are always in the equivalence class because you take the homotopy between them to be constant homotopy. Okay. So here I mean any isometry. So that's the first choice here. So whenever I take post composition, so in the representation theory, what that means is the following. So remember how we constructed this? We have phi star from fundamental group of S to pi 1 of fundamental group of X. And now if I have an isometry from X to Y, that isometry will give you another element, another homomorphism from here to here. And how does that change the group of Hall-Deck transformation? Well, here's the thing. So if you have two, so let me say this thing more clearly. If I have two subgroups, two discrete subgroups of the isometric group of upper half plane, whose quotient by the action of so suppose I have two subgroups of the isometries of the upper half plane, and then the quotient of H2 is the quotient of H1, then this isometry will induce a conjugation between H1 and H2. Then H1 and H2 are conjugates. Okay, so if two manifolds on the quotient are isometric, and this is, I think, in differential manifold we also studied this. I'm not sure, remember, but if you look at the set of all diffeomorphisms and you take two subgroups of diffeomorphisms which both act properly discontinuous, the quotient manifold is diffeomorphic, then actually they are conjugate by that diffeomorphism. Lift the diffeomorphism, that will give you a conjugate. Okay, so in other way, isometry on the second component, meaning isometry in this component, translated into group theory by conjugation. Okay, now conjugation in what? So here, this is the interesting part. Like here, if you look at yes, so here if you look at this thing, I'm taking a conjugation in PSL to R in the isometry of upper half plane. But the thing is, I really don't consider the isometry of the upper half, orientation preserving isometry of the upper half plane. If I just take conjugation by any element of the isometry group of upper half, doesn't matter whether it is orientation preserving and orientation reversing, because we are taking conjugate, it won't matter. You will still get a good representation. You still get a, in the quotient, you will still get a homeomorphic orientation preserving surface. So if you look at here, rather A being from PSL to R for isometry group orientation preserving isometry, I can take it to the whole isometry group of upper half. Yes, which is PGL to R. And the same will be true. No problem. Nothing will change. Exactly same thing will happen. So in other words, and I haven't talked anything about the homotopy of the marking. I'm just purely saying what happens if I have two markings where each one of them is differed by the other just by post composition of an isometry. So far, I'm just saying that. So post composition by an isometry is nothing but conjugating the homeomorphism by some element in the PSL to R or PG. Okay. So if I want to construct just that, I'm considering two markings which are equivalent just by a post composition with an isometry, not a homotopy. So the space that we get is space of all discrete faithful representation from the fundamental group of S to PSL to R, quotiented by the isometry group, the whole isometry group of upper half plane, which is PGL to R. And let me put this on box. So far we have received this. We got this. Now, what happens to this equivalence relation when I go from isometry to homotopy classes of isometry? What happens, rather than considering this post composing with an isometry, we consider something which is homotopy to an isometry. And this comes from an interesting fact in the upper half plane, and you can try to prove it. If two isometries of upper half planes are homotopic to each other, then they are equal. So in the homotopy classes of isometries, if you consider homotopy classes of isometries in the upper half plane, they are nothing but just the isometries. Nothing will change. And so the way to show the way you so it's the reason why this is why this happens, that in upper half plane the isometry, two isometries are homotopic if they are equal. So the reason why it happens is the following, and this is where this whole Gromov's part of idea of delta hyperbolic geometry comes into picture, that if you look to geodesics in the upper half plane, they can never be within a bounded distance of each other. And the action of isometry is completely determined by the action of the geodesic. So whenever you are looking at a homotopy of isometries, if you look at in terms of the action, what you are looking at is the homotopy classes of the geodesics. And on the upper half plane, every homotopy class, there is a unique geodesic. And this is a fundamental, very, very fundamental observation. This was actually done sometime back in 80s, I think, due to Gromov, that this whole idea of hyperbolicity comes from this feature. This is encoded in this particular feature. And in every homotopy class, there is a unique representative in some sense. In the upper half plane, every homotopy class, there is a unique geodesic. And this is the main character here. This is the main fundamental reason why once you take this quotient, you don't have to take any further quotient. So when we are thinking of marking in terms of representations, all we need is set of all discrete faithful representation quotiented by PGL2R. And that's it. That's the equivalence class of marking. So the theorem here is this thing is same as the Teichmiiller space of this. Whatever. So this thing here is nothing but the Teichmiiller space of as a set. And now this has a nice topology. Now you don't have to look into the compact open topology and all those things. Forget about that. Here, this is a finitely generated group. So you have a generator. You have A1, B1, A2, B2, A2G, B2G, right? And if you know where the generator goes, you are done. So each representation here is completely determined by a collection of 4G matrices here, right? And this is just 2 cross 2 matrices. So this whole object set of all homomorphism from pi1s to PSL2R, this sits inside some R to the power 4 into 4G. Okay. And then you quotient by this case. So this is space topology from this quotiented by this. So that gives you a space topology to the Teichmiller space. Any questions regarding this topology, or is discrete and faithful representation gives you markings, equivalence class of markings? I've just given you the brief proof. I didn't give you the details, but this is the idea of the proof. This is pretty much these are the technicalities you need for the proof. So first thing is properly discontinuously gives you discrete image. Secondly, the discrete image acts properly discontinuously. And the third thing is post-composing with a conjugate conjugation by an isometry is nothing but not changing the metric below. It's the same thing as saying I am not changing the metric below. And the third important thing which is the sort of the hidden feature in all of this, is when we are considering metric up to isometries up to isotopy or homotopy, what we are essentially doing are considering metric on the upper half plane. So upper half plane, 2 isometries are equivalent if they are homotopy. The same if they are homotopy. So on the quotient, if there is some homotopy in between them, then on the upper half plane, they will give you the same isometry. And by giving you the same isometry, meaning they are just differed from each other by conjugation. And that's where you take the quotient. You have already taken. Any questions? Any questions or comments? Okay, so now just to give you a prelude of what is the benefit of looking the object from this perspective. So this, I haven't told you this part. So now I have, let me just write this down. So now I have this Teichmiiller space, and this is okay. I can sort of write this down. Okay. So now we have mapping class group, right? So now look at the look at an element. Let's say F belongs to mapping class group of the surface. Okay. And I always make this mistake. So let me make sure I write it in the correct direction, because I always make this G or G inverse mistake. Sort of. Let me check which direction it goes. Otherwise, I will just simply write this down, and then please do check that I'm missing the action from other way around. Check 1 second. Yeah. So suppose F is from mapping class group, and so you take a marking from the Teichmiiller space. So what do we have here? We have from F to X, we have phi, which is a diffeomorphism, and X is a hyperbolic metric. Okay. If mapping class group is a class of homeomorphism, it's an isotopic class of homeomorphism. Okay, it's an isotopic class of homeomorphism. So therefore, you take a representative from F, call it F again, no problem. So then F gives you a map from S to S. Okay, this is just an isotopic class of homeomorphism. Correct? So therefore, you can define an action by composing this. Okay, so phi F acts on S x comma phi is nothing but the hyperbolic surface is same, you just change the marking. So the mapping class group acts on the Teichmiiller space. And now you can check that if you have two markings xc and yc, and if you change one marking by F and the other marking by F, both the markings by F, so if they are isotopic earlier, they will also be isotopic here, because F is not just a homeomorphism, it's an isotopic class of homeomorphism. So the isotopic class doesn't change. So moment you compose F with phi, if you have a y here and I compose y, will again be homotopic to the same object. So this action is actually well defined. Is this thing clear why the action is well defined? Remember, these markings are homotopic classes of functions, and F is isotopic class. So if you compose it by F inverse, you are not changing the homotopic class of the isotopic. Okay, so this is a genuine action, and the action is well defined.
EMCG and Pionov is they are somehow related, right? They're automorphism. Or...
Yeah, so that's I'm coming.
Because the Teichmiiller space you have defined completely algebraic way in the above, right? So
right,
this discrete faithful representation. So I am trying to look at all things in terms of algebraic way. So can you look at that?
Oh, so that you can always do, right? So you can always do. So let's say F is your mapping class group. So F gives you a map F star from pi 1s to pi 1s. So now you put this picture here. You have pi 1s which goes to phi1 of x, which is the group of Waldeck transformation of xp, which sits inside isometry group of upper half plane, which is PSL2R. And so now you have F star here. And so this gives you a row. So now the action is row composition F star inverse. That gives you another homomorphism.
Yeah, that is what I am asking. I mean, okay,
Yeah.
then one can study the whole thing in algebraic way, or
You can study whole thing in it.
I see. Okay.
You can study completely.
I mean, they reflect some result, right? I mean, if you come from geometry and you get some results, and you look at the algebraic results, which it corresponds to.
Right, but the see that this will correspond to, but the problem here is, you see, these representations are not completely algebraic. We have these two conditions. This is an algebraic condition. This thing is not an algebraic condition. This is a topological condition. Discreteness is not an algebraic property. So no matter which way you try to present the statements, there will be some kind of topology and geometry hidden inside. I mean, to say topology, not geometry. Actually, there will be some topology. Is it makes sense what I'm saying? So this discreteness is the major point here, major highlight. This is the topological point that you have to keep in mind.
Yes,
Okay.
that yeah. Okay. Yeah, you go ahead. Let's.
Yeah. Any other questions? Okay. So the mapping class group acts on Teichmiiller space. Okay. So we have a space here. So now let me go back to the picture here. So now we are in this situation. We have this Teichmiiller space that we have just defined. The mapping class group, it acts on Teichmiiller space. Then you get the moduli space. Well, there is this part, which is the properly discontinuous thing. And yeah, this is a result that you have to prove that the mapping class group actually do act properly discontinuously on the Teichmiiller space. But here in the properly discontinuity definition, you have to take the weakest form that you can possibly. You have to consider that every compact set, there are finitely many G such that GK intersection K is not free. That is the only definition. The moment you take free, the definition won't work. Yeah. So this do acts properly discontinuously on the Teichmiiller space to give you the quotient as a modular. Okay. So now we are sort of okay. So in the last 5 minutes, I just want to mention one thing. Right. If you look at this object, this Teichmiiller space, discrete faithful representation of phi1 is into PSL2R, quotiented by PGL2R. Just look at this. Okay. Now, if I ask you, can you give me so what is an element? What is an element? This is a equivalence class of homomorphism from phi1 to PSL2R. Okay. And what is the equivalence class? That whenever you have some kind of automorphism here in the PSL2R, in the inner automorphism, this gets absorbed by rho. This is the equivalence class. Okay. Now look at this, just this object. What are the other ways? Just this object, this sort of a representation up to this question. What are the other elements that can act on a space, on this space? See, let me rephrase this statement. So I have a fundamental group here. On the right hand side, I have a PSL2R here. I have incorporated the action of PSL2R on itself by conjugation. So whenever I have a element A in PSL2R, I take the conjugation by A, and that is already incorporated in the quotient. What is the other thing which can act on this representation, on a representation? So this is a general question. Suppose you have a representation from G to H. What are the always two actions that you define on this representation? What are the two ways you can always modify this representation? What are the two new ways by which you can always define a new representation?
You mean any dual or tensor product?
No, just look at this. You have given just group. So you have, so forget about everything else. Suppose you have two groups, G and H, and you have a homomorphism rho. What are the new ways you can construct another homomorphism out of this picture?
Something on G.
Right. So either you can do a homomorphism, you can take a homomorphism here and compose it, or you can take a homomorphism, yeah, or you can take a homomorphism here and compose it. So now the point is, in the discrete faithful representation, we have taken care of the automorphisms here, SL2R. So the thing left is to consider automorphism of pi1s. So the automorphisms of pi1s clearly acts on this space. Problem is, if I take a conjugation, we have already taken the action by conjugation. So if you take an inner automorphism here, it acts trivially on this space because we are already conjugating by a matrix. Is the statement clear? If I take a row, recompose it with an automorphism of pi1s, and the automorphism is an inner automorphism, nothing changes because we are already taking conjugation by PZ1. So the only automorphism which can act non-trivially on this space are the outer automorphisms of fundamental group. So the only automorphism which can act non-trivially on the Teichmiiller space are the outer automorphisms. Now, just look at these two pictures, and this is what Den-Nielsen theorem, Den-Nielsen-Beer, I think, forget about it. Anyway, Den-Nielsen theorem tells you, see, the mapping class group acts on Teichmiiller space. At the bottom, you know, outer automorphism group of fundamental group acts on the Teichmiiller space. Well, the theorem tells you these two are same. Mapping class group is nothing but the outer automorphism group of the fundamental group. That's what that's the perspective of theorem. You look at the Teichmiiller space in between, you look at two groups which acts on Teichmiiller space, and then you prove that these two groups are equivalent, the same. And so at the top, we have seen the mapping class group acts on Teichmiiller space pretty much by definition. And we have already seen that automorphism of fundamental group always acts on the Teichmiiller space. However, inner automorphism acts trivially. So the only thing that left is the outer automorphism group. And these two are same. Okay. So that is sort of one way to view the Den-Nielsen-Beer theorem, that the outer automorphism group. So let me write this down. So outer automorphism group of fundamental group of S is isomorphic to the mapping class group. Okay. A big warning here in this discussion: nowhere I have assumed S to be anything different than closed. So I'm not talking about boundaries. I'm not talking about functions. I haven't even defined what Teichmiiller space is for bounded surfaces with boundary or surfaces function. I'm not going to go in that direction. So there it is not true, first of all. Outer automorphism. So the moment your surface has a boundary or a puncture, this is an outer automorphism group of a free group. Pi1s becomes a free group, and this becomes an outer automorphism group of free group. This is a giant group. This huge group. This is way beyond our, like, the mapping class group is just a small subgroup of Right. You can identify which subgroup it is, but outermost group is much more complex. Yeah. So any questions? Any questions or doubts or anything?
Not questions, sir. That examples which I two markings are not equivalent.
Okay. Yeah. So what you can do here now is you can take a dent twist. Okay. To take an element of the mapping class group, you take a marking here, and you consider this marking, which is phi composition extreme. So these two will not be equal.
Okay.
Well, the easiest way to see this thing is just to check that on a curve they cannot be homotopy. So if there is an isometry between X to Y, they will give you a different homotopy classes. That's it.
Because the curve and its dent around its dent is not homotopy.
Not homotopy to each other. Exactly. That's the reason. So so this is just nothing. Yeah. This is another way to say this is dent twist is non-trivial element in that class. The same thing.
Thank you, sir.
Yeah.
This quotient is the moduli space, right? Teichmiiller
yeah, the quotient. Yeah, that is so the Teichmiiller space quotient is the So the Teichmiiller space quotient with mapping class group. This is the modular space. Modular space of the hyperbolic. This is the modular space of hyperbolic matrix up to isometry.
Yeah. So maybe I mean, give example of two different points of modular space.
Giving example of two different points in modular space.
Yes.
Oh, so you have to consider two hyperbolic metric on a surface which are not even isometric. So that's how we can define. Okay. So let me see how we can do that. Oh, I can take. Okay, so that's a bad way to. Okay. So I can take two distinct elements of mapping class group and consider their orbit, any points in their.
No, but they will be equivalent in the modular space, right?
They will be equivalent on the modular space, right?
I'm saying.
You will mean in the modular space they are not equivalent. Okay, so I have to think of a point in a Teichmiiller space. They are not in the same orbit. Okay, so they are not in the same orbit. Okay, how I can do that? So yes. So metric. How do I change the metric? So here is one way to do this in a very bad way. So you take a hyperbolic metric and you take a simple closed curve and you start squeezing that simple closed curve and you adjust the metric everywhere else. So you reduce the length of the that curve, of the smallest curve in some sense. We can take two different tessellations of H2, but how do we guarantee that they are not in the same?
I mean, you have to go through this Fenchel Nielsen coordinates, right? So
we can do that, but how do Fenchel Nielsen coordinates going to help to find two distinct elements in the modular space? So the only way I can think of it is you take two hyperbolic manifolds which has different systoles. That's what I'm telling you. Take the smallest curve here and take the smallest curve here. If you make one small, one large, then these two will be.
No. What I'm saying is that so this mapping class group, it is acting on this space, right?
Right.
And is this action properly discontinuous? So it has.
It is properly discontinuous. Yes.
But it has this
fixed point. So properly discontinuous in the sense that given a compact set K, there are finitely many elements such that GK intersection K is not.
So this definition.
This is the definition. Yeah. So that's what I said. Like unless you use this. Orbiford covering. Yes.
So, but
it's a finite.
You ignore the singular points.
Right. That's covering.
That's a covering map.
That's
So
allowed.
locally it is same as Teichmiiller space, right?
It is locally same as that.
Okay. So
It is
then,
locally same as, apart from cone points, it's locally same as that.
then I think you can give 2 points in Teichmiiller space. That will, I mean, locally you can do that thing, right? So on the
Yeah.
group, the Teichmiiller space, you give 2 points, then modular space you will also get 2 points.
Right, right. Yeah, so, but then we have to identify, right, how the look.
Yeah,
That's why you were saying that Fenchenians coordinate. Right. Yeah, use Fenchenians. So you twist along curve a little bit rather than taking the foot. Yeah. So here is an explicit. So yeah. So we give a nice example. So two hyperbolic metric are on the same twist orbit. If you take the full dent twist, rather than taking the full dent twist, take the surface and take a little twist it a little bit. Let's take half dent twist. Don't take full dent twist. Just take half dent twist. Just rotate it half and glue that. Create a new hyperbolic metric which is not equivalent to the old. You rotate it in any degree so that it doesn't come back. That's the point. Yeah. So that
yeah, but all this thing requires proof. I mean,
it does require. You have to prove it clearly. So that is, I think that will be the proof. Yeah.
I don't, without this thing, how do you produce new hyperbolic metric? Without knowing.
You can take this. Without using Fenchenius and coordinate.
I don't know how you. What the Shumon he was telling. Suppose I have 2 different tessellation.
Right.
Hyperbolic thing. But
how do we prove that they are in a different mapping class group orbit? I don't have much idea about it.
2 tessellation, it will be something. I mean, there should not be some map kind of thing. Which
Right.
Yeah, so you should not have some map from upward half plane to upward half plane, which is preserved. That map is isometric.
Right.
Except that that tessellation.
Right.
Right. If you don't have that thing, then I think you should be able to land something in this modular space.
Yeah. Suppose the side lengths are different. Yes. So Suman, as you said, yeah. So suppose the side lengths are different, then it is true, right? So the side lengths are two. Right. So you have to take 2 polygons, 2 fundamental polygons. The side lengths are essentially different. Then you will be able to, yeah. Then once there is a tessellation there, you will be able to produce 2 hyperbolic metric hyperbolic surfaces which are genuinely not isometric. Right. Okay. So then
So we stop here.
started. Yeah.
We